absolute convergence. Now, what is absolute convergence? Definition: the series A sub n is absolutely convergent if the series of the absolute of the term is convergent. Okay, that's the first definition. Now, if theorem, the series is absolutely convergent implies the series is convergent. Okay. Now, another one definition. The series A sub n is conditionally convergent if the series is convergent, but it is not absolutely. Okay, you can think of it this way. Absolute convergence is the strongest convergence possible. That's strongest. Conditionally convergent is in between, and divergent, of course, yes, divergent. So conditionally convergent is in the middle. Okay, now one classic example of conditionally convergent is alternating harmonic series. Okay, alternating harmonic series is conditionally convergent. Okay, what is alternating harmonic series again? Alternating harmonic series is this series. -1, actually no. -1 to the n, that's the alternator of 1 over n. Remember that? Okay, now this series is convergent, but the absolute is not. The series of the absolute, which is harmonic series, is not. Okay? So that's conditionally convergent. Now, from the theorem that we have here, we see that one way to show that a series is convergent is to show that it is absolutely convergent. Okay, we have a new test here called ratio test. That says that the following: if the next term over the current term in absolute sign, the limit is positive, of course, because that's absolute, right? And less than 1 implies the series is absolutely convergent. Okay, if it is greater than 1, if the limit is greater than 1, then the series is divergent. Now, if it is equal to 1, I'm sorry, I need to use this convergent to L. If the ratio convergent to L, then the series is either absolutely convergent or divergent. Now, if it is equal to 1, the limit is 1, then inconclusive. Nothing can be said. Okay, that's the ratio test. I really think at this point you need to, let me write down the other one. The other one is root test. Now, ratio test and root test are being used for if you have a series that is not always positive, I mean, sometimes positive, sometimes negative, and not necessarily alternating either. Okay, now the root test says that if the nth root of absolute A sub n converges to L, which is less than 1, then the series is absolutely convergent. Okay, so you see that the rule is actually the same with the ratio test. If the nth root of the absolute of the nth term is greater than 1, then the series is divergent. Now, if it is equal to 1, if the limit is equal to 1, then it is inconclusive. Okay, now let's look back into what we had so far. Because in 10.7, we need all these tests. But the thing is, like, you should not get confused though. Don't get confused. Okay, we have alternating series tests that says if the A sub n is decreasing eventually to 0, then the alternating series is convergent. Right? That's alternating series test. What else? We have integral tests. That says the following: if fx is a continuous superposition function of A sub n, and fx is eventually decreasing, it doesn't have to decrease to 0. Okay, even though you will see that's the case. Okay, it's just, you just need eventually decreasing. It's continuous superposition function of an on 0 to 1. I'm sorry, from 1 to infinity. then the integral from 1 to infinity of fx dx and the series a sub n from n equals to 1 to infinity are both convergent or both divergent. That's integral test. What else we know? Geometric series. If you have a series, the first term times the ratio to the n minus 1, okay, is convergent when the absolute of the ratio is less than 1, right? Does it make sense? Okay, and part of the integral test, let's not forgetting, we have the P series. That's the how we derive from integral test, P series. Okay, the series of n to the p is convergent when p is greater than 1, divergent otherwise. Okay, those are all the tests that we have learned. I think that's all. Is there anything else I forget?
I think you're missing the divergent test, the comparison test, and the limit comparison test, or the absolute
Oh yeah,
convergence.
that's right. Yeah, that's right. Divergence test is okay. I write it down. Test for divergence. Test for divergence. Okay, basically, a sub n not convergent to 0 implies the series is divergent. Okay, and then yes, comparison test. A sub n is less than equals to b sub n, but we want them to be non-negative, right? Okay. What else? Part A, if the series Bn is convergent, then the one in between must be convergent. However, if the series A sub n is divergent, then the bigger terms, the bigger series, the greater series will be divergent. Limit comparison test. Says, of course, they have to be non-negative terms, right? Okay, so A sub n, B sub n is greater or equals to 0. And A sub n over B sub n is convergent to a constant, call that L, where this L is finite. This is actually the notation to say that the L is finite. Okay, to say the L is finite. And of course, it has to be positive, right? Positive or 0. Then the series A sub n and the series B sub n are both convergent or both divergent. Do I miss anything so far? That's for actually for next section though. Okay, so for 11.1, 11.7 later on. 11.7 later on, I will copy paste this. Okay, what I don't want to happen is you confuse. Notice that the test that we learned so far, especially the limit comparison test. Limit comparison test, the ratio of the limit can be any positive number. The ratio of the limit can be any positive number, as long as it is finite. Okay. However, ratio tests, the limit has to be less than 1. Okay. Root test, the limit has to be less than 1. Okay. Now let's start. Question number 3. We have, the question is, determine whether the series is absolutely convergent, conditionally convergent, or divergent. Number 3, the series n over 5 to the n. Is it convergent or divergent? Solution. It's already positive term. It's already positive term. Let me use the ratio test. Okay, the ratio test will be absolute of a sub n plus 1, the next term divided by the current term. Right, that is equal to n plus 1 over 5 to the n plus 1 times the reciprocal, which is 5 to the n over n. Actually, you will see that I don't need the absolute value, right? Gada-bum, gada-boom, I have n plus 1 over n times 1/5. I can pull the 1/5 out, right? And n plus 1 over n, there I have 1/5 times 1 plus 1 over n over 1. This is convergent to 1/5, is it right? Okay, so by ratio test, which is less than 1, by ratio test, this series, and be explicit again, please be explicit. N equals to 1 to infinity is absolutely convergent.
Thomas, can you explain what you did in the second line?
So this is a sub n plus 1 is n plus 1 over 5 to the n plus 1, is it right?
Mm-hmm.
Okay, now then what happened to the denominator? Divided by n over 5 to the n, is it right?
Yeah.
Now that's the same to multiply by the reciprocal.
Right.
Yeah, this guy multiplied by the reciprocal of this.
Okay. Yeah, I understand that part. I guess I guess maybe I should have really been saying if you could explain the third line then, because how did you get, or how do you know when to, like, what to eliminate, I guess. I don't know if that's the right word.
It's 5 to the n and 5 to the n plus 1.
What is that? I don't understand. How do you
That's 5 to the
that?
n over 5 to the n times 5.
Oh, okay.
Right?
Okay.
Yeah.
And that explains a lot.
Now, because the series is absolutely convergent, therefore it is convergent. Okay. The thing is, if the question were show that this series is convergent, you need to be explicit saying that after you say that it is absolute convergent, after you say that this series is absolute convergent, you need to continue saying that the series is convergent. Okay, I know a lot of students just say, well, but Thomas, it is absolutely convergent, so it must be convergent. I understand, but technically speaking, the question is it convergent or not? Okay, so after you get that the series is absolutely convergent, you need to continue saying if the series is convergent or not. Okay, that's for number 3. Let's see number 5. We have this, and from 0 to infinity this time. Solution, again, I will use ratio test. We use ratio test if, I tend to use ratio tests if the series, the terms of the series, sometimes positive, sometimes negative, or if we do the ratio, a lot of things cancels. Believe it or not, this ratio test also work if you have geometric series. If you have geometric series, then this ratio test also works. In other words, if you have geometric series and you misapplied, instead of you look at the ratio, you look at the ratio, instead of the ratio R to be less than 1, you actually look at the limit of the ratio of the terms. Then you will see you will come up with the same conclusion. Okay, now let's see, I will look at the ratio, a sub n plus 1 over a sub n. That is the ratio of -1 to the n plus 1 over 5 times n plus 1 plus 1 over because it's absolute value, then a lot of things cancels, right? So we get 5n plus 1 over 5n plus 6. Okay, I'll divide by n on the top and the bottom. This converges to 5 over 5, which is 1. So root test, ratio test is inconclusive. Okay. Now, of course, if the result is inconclusive, you don't write that in your answer, right? You cannot tell anything. Okay, I just show you here that the ratio test is inconclusive. Then you need to come up with another method. Okay, but after all, that's alternating harmonic series, right? So let's go back and see that this is that's alternating series. So I will just use alternating series test. Okay, where the Bn is the positive part. Okay, we know this is convergent to 0. Right, alternating, convergent to 0. Okay, so this series is convergent. But is it absolutely or just conditionally? Now take a look on the absolute. Is that convergent or not? How do you know that this is convergent or divergent. So many ways you can use integral tests. Okay, you can use integral tests. What else? I will use comparison tests. I will say that this is greater equals to the series from 0 to infinity of 1 over 5n plus 5. Don't get me wrong, this is only one way to do it. Okay, you may use integral tests. Okay, so let fx equals to 1 over 5x plus 1, boom, integral from 0 to infinity of 1 over 5x plus 1 dx. You will see this is divergent. Okay, let's you show the work there. Now, but another way to do it is this. Notice that this guy here is greater than if I divide by a larger number, right? I divide by a larger number. But why you do that, Thomas? Well, manipulation. Because this is n equals to 0 to infinity of 1 over 5 times n plus 1. I can change that n plus 1 to be m. So instead of n, let me call that m from 1 to infinity instead. You see that? Okay, let's start from 1 over 5m. Now this is equal to 1/5 of a harmonic series. Okay, since this series is divergent by harmonic series, then 1/5 of that is also divergent. By comparison test, then the series 1 over 5n plus 1 from 0 to infinity is divergent. So don't forget, the main topic is this one. Is conditionally convergent. Okay, so you see that the work actually gets longer. Okay, you can eliminate this because I tried to use ratio test and it didn't. It's inconclusive. You can eliminate this. Okay. Now, once you get that the absolute the series is convergent, then you need to see if it is absolutely convergent. And in this case, you see it is not. That's for number 5. Number 7. It seems like this is a geometric series, but it is not really geometric series because we have k here. If it is geometric, then this will be a coefficient, a constant, okay, but not variable. So is this geometric or not, Thomas? You will see later on it has something to do with geometric tests, but for now we will say it's not. Okay, now then, how do we show that this is convergent or divergent? I will first show that a sub k plus 1 over a sub k. Basically, I do ratio tests. Okay, This is equal to k plus 1 times 2 over 3 to the k plus 1 over k times 2 over 3 to the k. That is equal to k plus 1 over k times 2 over 3. See, this guy here, 2 over 3 to the k cancels, becomes only 2 over 3. That's the extra factor we have on the top. Okay? And then this guy gives us this. And then I divide the top and the bottom by k. This converges to 2 over 3, which is less than 1. Now you may wonder, Thomas, why do you use ratio tests while the terms are all positive? Well, ratio tests actually applies to all terms. It's more general compared to comparison tests, and therefore more general compared to limit comparison tests. Okay, comparison test, limit comparison test requires the sequence to be non-negative, right? Okay. Integral test requires the continuous superposition function to be non-negative either, right? Now, but ratio test does not require the terms to be non-negative. Okay. Now, because the terms doesn't have to be non-negative, does not mean the terms cannot be positive. No, it's okay. You still can use that. Okay, you still can use that. Now from here we see that because the limit of the ratio is 2/3, which is less than 1, so we conclude right away that this series is absolutely convergent. That's for number 7. Now, I may end up doing too many problems later on. So would you like to choose some questions for me to do after number 7? Give me 5 questions. Between number 9 to number 30. If we have more time, then we will do more later on. Would you like to choose? While waiting, let me do number 13 first. We have this series from 1 to infinity of 10 to the n over n plus 1 times 4 to the 2n plus 1. This is 11.6.
Thomas, after that one, can you do number 17?
Okay. Okay, let me write it down. Number 17.
And number 21.
Number 21. Number 19. And somebody, Robert, say number what? Number 24. Or Matthew say number 24. Okay, so we get 5 questions here. Later on, if you have more, we do it later. So let's take a look on the ratio. That's 10 to the n plus 1 over n plus 2, 4 to the 2 times n plus 1 plus 1. That's a sub n plus 1 divided by the current term, which means multiplied by the reciprocal, n plus 1 times 4 to the 2n plus 1 over 10 to the n. It's all positive terms, so I can simplify this guy with this guy. Give me what?
This gives you 10, right?
Where? On the top or at the bottom?
At the top.
On the top. Okay, and then we have n plus 1 over n plus 2. That's something we cannot simplify. So let me bundle them. Okay, that's the yellow one. Okay, now what happened with the 4? Let's write it down first then. So this will be 4 on the top, 4 to the 2n plus 1. At the bottom, we have 4 to the 2n plus 3. Is it right?
Yeah.
Which will give me, I don't need the absolute sign anymore. That will be 10 times n plus 1 over n plus 2 over, times 1 over 4 squared, right? Which is 16. That will be 10 over 16 times 1 plus 1 over n over 1 plus 2 over n. This will be convergent to 10 over 16 or 5/8, which is less than 1. So the series, is it n or k? N. From 1 to infinity of 10 to the n over n plus 1, 4 to the 2n plus 1 is absolutely convergent. That's for number 13. Number 17. Let me move that somewhere to the middle here. That's what I need to do later on. Number 17. The series from 2 to infinity of -1 to the n over natural log of n. I think this will be inconclusive if I use ratio test. If I use ratio test, it will be inconclusive. Okay, I go ahead with the series. So this is from 2 to infinity, that's alternating series. Is an alternating series with Bn equals to 1 over ln n, right? Now we know this is convergent to 0. So can I say that this series is convergent? Actually, I can say even more. It is decreasing down to 0. Okay, proof. Well, ln n is greater than 0 for n greater equals to 2, right? Okay, it's positive. Okay, now n, ln n must be less than natural log of n plus 1. At the same time, it's positive. Therefore, the reciprocal reverse the inequality. Okay, and of course, 1 over ln n is convergent to 0. So I proved two things, that it is decreasing, second, convergent to 0, right? By alternating series tests, this series is convergent. The problem is, will that convergent absolutely or conditionally? Take a look on the absolute. The series, actually from 2, absolute of -1 to the n over ln n will be equals to the series of 1 over ln n. We know one thing. Note that even though ln n is positive, it is always less than n. It is always less than n. Actually, it is for every n. Okay, natural log of n has this shape, right? Okay, while n has this natural log of x is that, by while y equals to x looks like this, right? Do you see that? Okay, now consequently 1 over natural log of n must be greater than 1 over n. Is that right? Okay, so the series 1 over natural log of n is greater than the harmonic series. By harmonic series, this is divergent. By comparison test, the series from 2 to infinity of 1 over ln n is also divergent. So, going back to the original one, okay, -1 to the n over ln n is convergent or divergent?
Wouldn't it be divergent?
No, this series is convergent.
Oh, I'm sorry, I got kind of confused.
Okay, the alternate one is, the alternate is convergent. The absolute is divergent. Yes, what we want to conclude is it conditionally convergent or absolutely convergent? So don't lose track, okay? Don't lose track. The question is it divergent or absolutely convergent? If neither one, if it is not absolutely convergent, yet it is convergent, then it is conditionally convergent. So this series itself is convergent, but not absolutely. Okay, that's for number 17. Let's see number 21. Let me do it here. We have the series from 1 to, hold on. Do I have number 19? Yeah, number 19. I do number 19 first. The series from 1 to infinity of cosine n pi over 3. This is where absolute value becomes necessary. over n factorial, n pi over 3. Now then solution. Okay, absolute of n plus 1, I mean the n plus first term over is the nth term will be the numerator. I will have cosine n pi plus pi over 3 inside the cosine over n plus 1 factorial divided by cosine n pi over 3 over n factorial. Now, you may get distracted with the cosine. What should I do with the cosine? What should I do with the cosine? Don't worry too much. Okay, this is cosine n pi plus pi over 3 over cosine. You know what? Now I realize it may not be true. No. Let me show you what's wrong with my thought. Earlier, I was thinking to make it ratio. And we have n factorial over n plus 1 factorial. Right? Now, I want to say earlier, I want to say that this guy is at most 1 inside the absolute. And this is also at most 1. This guy will becomes 1 over n plus 1, right? Okay. I wanted to say that this is actually at most 1, but that's actually not true. I cannot do it this way. I cannot do it this way. This is not true. This is not true. Okay. For example, if the top one is 0.7, which is less than 1, and the bottom one is 0.2, which is also less than 1, but you see the ratio is 3.5, which is more than 1. Right? So I cannot argue this way. I cannot argue this way. Okay. We don't know what is this. Okay. I cannot argue this way. Now, so I cannot use ratio tests. Let's take a look on the absolute value. The series n plus 1 to infinity of cosine n pi over 3 over n factorial, this is for sure less than or equal to at most 1 over n factorial. Right? Now, if I can show that this series here is convergent, then this will be convergent, and therefore this series, original one, is absolutely convergent. Let's say the logic again. Okay, if I can show that this is convergent, and by comparison test, this is convergent, then this is absolutely convergent. Okay, now, so I will do ratio test right now on the 1 over n factorial. Okay, will perform, maybe I just say right away, ratio test on this series. So we have so many series to deal with here, right? Okay, so the n plus first over n term will be 1 over n plus 1 factorial over 1 over n factorial. I know it will be positive, but show that properly. This will be n factorial over n plus 1 factorial. This is 1 over n plus 1. That's convergent to actually 0. Right? Which is less than 1. Okay? So, by ratio test, this series is actually absolutely convergent. Let's just call that convergent. Factorials cancel each other out. Here's the thing. N factorial means n times n minus 1 times n minus 2 all the way down to 2 times 1. Now the denominator is n plus 1 factorial, which means you start from n plus 1. You see that? Okay, that's why this part here cancels. You can also think this way. N plus 1 factorial is actually n plus 1 times n factorial. Right? Okay. So let's say, for example, 7 factorial is 7 times 6 factorial. Do you see that? Now let me go back. Okay, now, so by ratio tests, then this guy is convergent. Now, then what makes this convergent? By what this is convergent? Oh, nobody can tell me.
Wasn't that the comparison?
That's right, by comparison tests.
Oh, sorry, I didn't know you were asking a question.
Yeah, it's by comparison test. Okay, and therefore, by definition, the series, the original series, cosine n pi over 3 over n factorial is absolutely convergent. Okay, that's the definition of absolute convergence. If you apply absolute value on the terms and it is still convergent, then without that absolute value, it is absolutely convergent. Okay, that's for number 19. Let me partition that here and partition that here. Number 21. The series n squared plus 1 over 2n squared plus 1 to the power of n. Oh, you know what? It reminds me of this. Okay, two of you.
The root test?
Yeah, we will use root test. But two of you say the following. Okay, square nth root of 4, for example, is convergence to 0. That's not true, though. It's actually not true. Okay, that's why we need to prove. Okay, that's why we need to prove. But it is not true. It is not convergent to 0. It's actually convergent to 1. Now, what is the proof? Natural log of 4 to the 1 over n is equals to 1 over n natural log of 4. That's convergent to 0. Okay, but then what happened to, if this is our y here, right? If that's our y, then 4 to the 1 over n, which is nth root of 4, is equal to, is convergent to e to the 0, which is 1. Right? It's the natural log of this expression, that is convergent to 0. Okay, but not that sequence itself convergent to 0. No, it's the natural log of that is convergent to 0. Okay, look at my solution for the your test 3 again. Okay, but the two of you actually make a quite terrible mistake. I was like, well, once you did part A correctly, you almost get it for that question. Part A was like, I forgot what's the question. I think it's 3 nth root of 3 plus what? Natural log of n or cosine of n, something. Cosine of n, I think. I forgot precisely. Oh, yeah. Now, then in part A, I asked you, in part A, the question was 3 plus cosine n over n. And most of you are actually correct that it is convergent to 0. Okay, all you need is actually to say that it is less than equals to 4 over n, right? And this convergent to 0, therefore the sequence itself is convergent to 0 by squeeze theorem. Okay, now in part B, yeah, those two questions are actually related. Okay, in part B, let y, my main question is I want to ask if the nth root of 3 plus cosine n is convergent or not. That's actually my main question. But I think if I ask that question may be too long. So I break it into two parts, part A and part B. Okay, so let y equals to 3 plus cosine n to the power of 1 over n. Now then natural log of y will be 1 over n natural log of 3 plus cosine n. Okay, now then apply the limit. Limit n goes to infinity of natural log of y equals to limit n goes to infinity of natural log of 3 plus cosine n over n, and we know that is equals to 0. Okay, but on the other hand, the left hand side, you switch the limit and natural log. Okay, so limit n goes to infinity of y is e to the 0, which is 1. Okay, that's actually the work. Now, some of you incorrectly applies L'Hopital rule here. No, you can't. No L'Hopital rule when it is sequence. That's one. Second, another reason you cannot apply L'Hopital rule is this. This is not going to, this goes to infinity, that's true. But natural log of 3 plus cosine n is not going to infinity. It's bounded. It's bounded by natural log of 4 above and below by natural log of 2. It's not going to infinity. So applying L'Hopital rule there has two big problems. Okay, first, those are sequence. They are not continuous functions. Okay, so they are not differentiable, at least technically. Second, even if you change them into continuous superposition function case, it's not indefinite form. Okay, it's not that infinity over infinity case. Okay, so no, you can't use L'Hopital rule there. You can't use L'Hopital rule there. I wonder where I saw that question. Oh, you know what? I want to share this with you. I really need to share this with you before I forget. Somehow I think I shared that in my lecture, but maybe not. Totally forgot. Hold on. Let me go back here so that I don't lose my focus. I want to show you where you can study from not only my old tests, but also, why did I cancel that? Also from the past. You go to my website, harjuno.com. Do you see what I'm doing here? Yeah. Okay, and then of course you click my face. Hold on, why it takes so long? Wait, is the internet working? Yeah, it works. Okay, now you go to Test Playground, USC Past Finals. Okay, and then you look at their calculus 2. Their curriculum is slightly different from ours. They don't have parametric. I think they don't have parametric functions, but they do have polar functions. Okay, but they have a pretty good questions on. I show you an example on sequence series. So sometimes I pick problem from there. You see, this is your last question, right? Okay, I took it from there. Of course, I can easily modify that. Okay, let me pick another one. Let's say this one here. Does it have solution? No, it doesn't have solution. So what you can do is you do them and then you ask me. Okay, which question did I? Oh, I didn't take any question from here. This is already series. Sequence, any sequence, any sequence. So you see, this one is partial fraction decomposition, right? Plus, this is what's that? The integral to infinity, right? So there are two problems in this integral here. Okay, you need to do partial fraction decomposition, and then you need to use limit to infinity. Hold on. Which question did I use? Not that one, even though I can. Yeah, we will have this kind of question in future. Let's see. How about spring 08? No problem. No problem can be taken from here, apparently. Okay. So that's where I sometimes take my problem. Of course, not only from here though. I know one of my former students studied so hard from all these tests. Okay. And then he got so disappointed when I pick questions from other university instead. I say, no, you don't need to be disappointed because I think this is the other one question that I asked, huh? Right? Yeah, you don't need to be disappointed because even though the questions are very different, but the concepts are actually still the same. So he still got a very good grade when it came to the test, even though he say, Thomas, none of this problem I have seen before. So, well, so what? Well, anyway, that's what happened at that time. Now let me go back to this number 21. Yes, if you have on the exponent, you have n as the counter, n at the same time, it doesn't look any close to geometric series, then you want to consider root test. Okay, then you want to consider root test solution. The nth root of absolute a sub n is the nth root of n plus 1, n squared plus 1 over 2n squared plus 1 to the n. But this is n squared plus 1 over 2n squared plus 1, right? The nth root cancels the n. And of course, inside is positive, right? So I can get rid of the absolute value. And then divide by n squared on the top and at the bottom. Now this is convergent to 1/2, which is less than 1. So by root test, the series, again, every time you say the series is convergent or divergent, absolutely convergent, be explicit, write that series down again. But Thomas, you know what I mean? No. I have one wife, that's one too many. If you don't say it clearly, don't expect me to understand it clearly. In fact, if you don't say it clearly, expect me to purposely not understand it clearly. Okay, Thomas, you're so evil. Welcome to Thomas class. No. Eventually, you know that when it comes to scientific community, we cannot just say this or that. You need to be specific. Okay, this series, that term, right? Okay, write it down if you do it in writing. That's for number 21. What else? Number 24. And then after that, I will take a break. And of course, after the break, feel free to ask me further question. Okay, we have this series here from 2 to infinity of negative 2n over n plus 1 to the 5n. Oh, this is alternating, but the magnitude is greater than 2. Okay, let's do root test. Let's do root test. Because we have exponent n in the terms. This is the nth root of absolute of negative 2n over n plus 1 to the 5n. That is equals to 2n over n plus 1 to the power of 5. Is it right? Now this is equal to divide by n on the top and at the bottom. This is convergent to 2 to the 5th, which is 32. That's greater than 1. So this series is divergent. Okay, let's take 10-15 minutes break. 10 minutes. We come back at 8:46, And then we do more problems from here. Of course, feel free to let me know which problem you want me to go over. Any other question you want me to go over? Could we do number 24? We did number 24. Oh, sorry. I was looking at number 22. Oh, thank you. Oh, if you don't say that, I don't realize that. Thank you. So this is actually number 22. My bad. That's number 22. Number 24. Number 24, the series from 1 to infinity of 2n factorial over n factorial squared. Ooh, that's ugly. Solution. I think this is not convergent to 0 though. Okay, a sub n, which is 2n factorial over n factorial squared, is 2n times 2n minus 1, 2n minus 2, all the way down to n plus 1 times n factorial over n times n minus 1 times n minus 2 all the way down to 1 times another n factorial. Okay, which is equal to the n factorial cancels. So basically it becomes the following. The first term here, that will be 2. Okay, that will be 2, the first term. This term here must be greater than 1. So I will bound it below. Must be greater equals to 1. This is 1, 1, n plus 1. Yeah, I want to say that this guy for sure is greater than 1. This guy for sure is greater than 1. Is it right? Now the last term, however, the last factor is exactly n plus 1. Now the thing is, this guy here, so this is 2 times n plus 1, this goes to infinity, right? So by divergence test for divergence, this series is divergent. Okay, it explodes to infinity. In fact, I somehow think we can say this is greater than 2. I can change all of this to 2. Yeah, 2n minus 1 over n minus 1. 2n minus 1 plus minus 2 plus 1 over n minus 1. So this is 2 plus 1 over n minus 1, right? Do you see that? Okay, if you have minus 2 here over 2, then it will be minus 4 plus 2, right? So it is still greater than 2. Okay, so it actually explodes to infinity quite fast. Okay, anyway, I bound it below by infinity, so the sequence goes to infinity, therefore the series goes to infinity. I don't need this. I don't need that strong one. Okay, that's for number 24. Any else? Number 26. Number 26, the series from 1 to infinity of 2 to the n squared over n factorial. Ooh, wow. No clue. Let me use ratio test. So a sub n plus 1 over a sub n. That's 2 to the n plus 1 squared over n plus 1 factorial times n factorial over 2 to the n squared. It's all positive numbers, so I can just ignore the absolute. Let me rewrite them. This is 2 to the n squared plus 2n plus 1. This is n plus 1 times n factorial. This is n factorial here, 2 to the n squared. So on the top, I have 2 to the 2n plus 1. At the bottom, I have n plus 1, right? Because this cancels. Okay, this also cancels, right? Now on the top, I will get 2 times 4 to the n over n plus 1. Oh. How to do this? I know this goes to infinity, but why? That's something I will answer later on, but at least from here we get, so by ratio test, this series is divergent. Okay, now let's prove this part here. Let the proof, let fx equals to 2 times 4 to the x over x plus 1. Okay, note that this is the continuous superposition function for that sequence, for this sequence. Right? Now, what is the reason I want to use continuous superposition function? That's because I need to use L'Hopital rule. But to use L'Hopital rule, I cannot just do it from the sequence. I need to do that from the continuous function. Oh, sorry. I forgot the limit here. Then I apply L'Hopital rule. At the bottom, I have 1. On the top, I get 4 to the x times natural log of 4. Right? Which goes to infinity, which is equals to infinity in this case. So by continuous superposition function, a sub n, which in this case is 2 times 4 to the n over n plus 1 goes to infinity. Okay, that's for number 26. Any else? No more. Number 37. Oh, by the way, before I forget, number 31. Number 31. This is a series whose terms are defined recursively. Okay, a sub 1 is 2. A sub n plus 1 equals to 5n plus 1 over 4n plus 3 of the previous term. Okay, now, so determine whether the series convergent or divergent. Convergent or divergent. Okay, solution. Notice that the n plus first term divided by the current, the n term is absolute of 5n plus 1 over 4n plus 3, which is 5n plus 1 over 4n plus 3. Divide the top and the bottom by n. Which converts to 5 over 4, which is strictly greater than 1. Right? So the series is divergent by ratio test. Okay, so what that tool has to do in this case, Thomas, because you didn't really use this at all. This is just to make sure that the n term is positive. Okay, if the first term is positive, notice then you will always multiply by a positive term, by a positive coefficient, right? Okay, so using a sub 1 to be positive, okay, then a sub n will also be positive, since 5n plus 1 over 4n plus 3 is positive. Right? The second term will be 5n plus 1 over 4n plus 3 multiplied by a positive number. Right? The first term is positive. The second term is 5 times 2 plus, 5 times 1 plus 1 over 4 times 1 plus 3 multiplied by a sub 1. Right? But this is positive, so a sub 2 is positive. right? Now, then therefore you will see a sub 3 will also be positive. Why? Because the coefficient here is positive and this is also positive. So recursively, then all a sub n will be positive. Oh, I look at number 33. I start thinking if I should try that. Let me try number 33. Number 3, Bn is a positive sequence that is convergent to 1/2. Determine whether the given series is absolutely convergent. So determine whether the series from 1 to infinity of b sub n to the n cosine n pi over n. Solution. Let's take a look at this series here. If I put absolute value, cosine n pi, actually cosine n pi will be alternating, positive, -1. Okay, so this will be the series b sub n to the n over n. What else can we say here? I cannot bound this above though. Yeah, I cannot bound this above. How to go on from here? Oh, you know what? We can do not ratio test, limit comparison test. Let's try. Is it really? No. Ratio test. So by ratio test, I wonder if it works. By ratio test, b sub n plus 1 to the n plus 1 over n plus 1 times the reciprocal. This is equal to, I'm sorry, this is just b to the b sub n to n. So this will be, I don't need absolute value anymore. Let me take care of the end first. I know this part will convergent to 1. Okay. And on the top, I have b sub n plus 1 to the n times b sub n plus 1 over at the bottom b sub n to the n. This is equal to n times n plus 1. I think I can bundle this together. So the n times b sub n plus 1. I think that's the furthest I can go. This will go to, you know what, let me do this first. This is 1 over 1 plus 1 over n. The first factor goes to 1. The last factor goes to 1/2. I don't know about this. I really want to say that's convergent to 1. But how do I argue about that? I really want to say that's 1, but honestly, I can't really. Basically, later on, I want to claim that this is actually becomes 1, which becomes 1/2, which is less than 1. Therefore, this series is convergent by ratio tests. Therefore, this series here is absolutely convergent. Well, I get stuck here. I get stuck here, or maybe other way, but I get stuck here. How do I argue that the ratio will be 1? The thing is, like, I have to the power of n here. That's actually make it troublesome. Now you may wonder, Thomas, why can't we just claim that's 1? Here's the thing. Here's the thing. You remember that we have this case here, 1 plus 1 over n to the power of n, right? Now, the inside here, if you do them separately, this is convergent to 1, right? Okay, so you may think 1 to the infinity is 1, but it is true, 1 to the infinity is 1. The thing is, like, this is not 1. Okay, we remember this is actually convergent to E, not to 1. Okay, not to 1. That's why I cannot conclude that this is going to 1. No, I cannot. Yeah, 1 to the infinity is indeterminate under limit condition, right? So we cannot say it is actually 1. I cannot. I mean, I wish I can, and we get the end of story, right? Okay, but this is still a question mark. I know this one is going to 1. That's easy. This one going to 1/2 according to what they say. But that's not true for this. Okay, let me think about that later on. You know what? Let me pause the video first and then think about it. I don't know the answer. Who knows my approach is actually wrong, right? Well, let me pause this first. Okay, I just realized that I need to record it. So let me try root test instead. When I do root test, this is what I get. The thing is, I don't know what happened to the denominator. Right? The numerator, I know it will go to 1/2. But what happened to the denominator? So consider let y equals to the nth root of n, that is n to the power of 1 over n. So the natural log of y is 1 over n natural log of n. Now the limit as n goes to infinity of natural log of y is limit n goes to infinity of natural log of n over n. Yeah, you will see this is actually going to 0. Right, that's equals to 0. But we need to use continuous superposition function though. Anyway, I do it by faith that this is 0. Therefore, natural log of limit n goes to infinity of y is equals to 0. So limit n goes to infinity of y is e to the 0, which is 1. In other words, nth root of n goes to 1. So this is 1, which is 1/2. So by root test, the series b sub n to the n cosine n pi over n over n is absolutely convergent. Actually, I need to say something in between. Yeah, so I need to say that the series from 1 to infinity of b sub n to the n over n is convergent. Okay, that's by root test. And therefore, the series is absolutely convergent. Okay. Well, in the next half an hour, let's do some problems from 11.7, which is basically the combo of all tests on convergence for series. Convergency tests for series. 11.7, that's the combo. Okay. If you remember, somewhere in the past, we have that strategies for integral. Right now is strategies for testing series. Okay, 11.7, you choose questions. Choose maybe 5 questions, maybe. Okay, but I remember I kind of get stuck for number 38, as I remember. I get stuck with number 38. So don't choose number 38 yet. Okay, or maybe number 36 also. I forgot which one I get stuck. Okay. Between number 1 to number, let's say number 1 to number 19. Choose maybe 3, 4 questions. Nobody say anything. Oh, okay, let me see. Number 19, number 36, number what? 15? 15, 19, yeah, 15 and 19. Number 15 and number 19 here. Any else? Number 12. So let me insert to number 12. Number 12, the series k equals to 1 to infinity of 1 over, this one is actually on the easy side, k squared plus 1. Show that it is convergent or divergent, right? Okay. I will show this, that k squared is definitely less than k squared plus 1. Square root of k squared is less than square root of k squared plus 1. But still positive, of course, right? Does it make sense? Okay, now then we do the reciprocal. Now it has to be positive though. Both of them has to be positive because the reciprocal may not be true. Okay, the reciprocal may not be true. Let's say if one of them is, let's say, -1 and the other one is 3. -1 is less than 3. The reciprocal, it's still, you maintain. Okay, you still maintain the inequality. So, but if one of them is, both of them positive, then the reciprocal, you reverse the inequality sign. Okay. That's why we need that to be. Actually, if both of them negative, still also correct. It's still correct if both of them negative. Okay, now for that, then if I multiply by k, 1 over k both sides, then the inequality being maintained because 1 over k is positive, right? So basically what happened is, so let me continue here, then the series 1 over k square root of k squared plus 1 is less than equals to the series of 1 over k squared. Okay, now, but the series 1 over k squared is convergent or divergent? And why? P series, P equals to 2. Okay, so by comparison test, the original series that we talk about. So be explicit again, please be explicit. Okay. That's for number 12. Let's see number 15. The series from k equals to 1 to infinity. I have 2 to the k minus 1 times 3 to the k plus 1 over k to the k. What the? Oh, wow. I think I need to rearrange this a lot though. Okay, let's do that. I need to massage that first. Okay, so this will be the series k equals to 1 to infinity. This is 2 to the k over 2. 3 times 3 to the k and k to the k. Right? Okay, which is equal to the series k from 1 to infinity of 3 over 2 parentheses 2 times 3 over k to the k. Is it right? I can factor 3/2 out, and then from there I will use root test. Okay. By root test. Or you can also say test the root. Okay, the kth root of 6 over k to the k is 6 over k, and this is convergent to 0, which is less than 1. Okay. So by root test, as we have mentioned earlier, 6 over k to the k from 1 to infinity is convergent. Yeah, multiply by 3/2. It is still convergent. So the original, let me copy the series again. So a lot of massage here, huh? Is convergent. In fact, it is absolutely convergent, but it's not necessary to say it's absolutely convergent because the terms are already positive. That's for number 15. Where's my number 19 earlier I wrote? Okay, let me write number 19 here. That's an alternating series, n equals to 1 to infinity, -1 to the n, natural log of n over square root of n. This series is alternating series. With Bn, the positive terms to be natural log of n over square root of n. Now we need to show, because it's alternating series, we need to show that this is convergent to 0. Want to show that this is convergent to 0 and decreasing. Okay, and decreasing. So to show decreasing and convergent, let's do continuous superposition function. Let fx equals to natural log of x over square root of x. Now this is continuous on what we need is actually just from 1 to infinity, right? In fact, it is actually continuous from 0 to infinity, not including 0. Okay. Now f prime x equals to x at the bottom, 1 over x times square root of x minus 1 over 2 radical x times ln x. Multiply the top and the bottom by x. I will get radical x minus maybe 2x instead. So I will get 2 radical x minus radical x natural log of x over 2x squared. Factor square root of x, 2 minus natural log of x over 2 to the 2 times x radical x. But the denominator is positive, right? Okay. 2x radical x is positive on 1 to infinity. It's actually positive on 0 to infinity. Okay, now 2 minus natural log of x will be negative. Where? 2 less than natural log of x, e squared is less than x. So let's use x greater equals to 3. Okay, so f prime x is negative when x is greater equals to 9. In other words, this fx is eventually decreasing. Okay, decreasing to what? Let's find the limit. Limit of fx for x going to infinity . This is by L'Hopital rule. It's 1 over x. This is 1 over 2 radical x, which will be 2 radical x over x. Now don't do L'Hopital rule again. You can just simplify that. Okay, this is 2 over radical x, but this goes to 0. So the function fx is continuous and eventually decreasing down to 0. So the sequence natural log of n over square root of n also convergent to 0. In fact, it is decreasing, right? Eventually decreasing down to 0 by alternating series tests. The series is convergent. Just for fun, follow up for fun maybe. Can you tell right away if this series is convergent or divergent? Why? That's true. It's divergent, but why? Let's take a look on the series. This is greater equals to 1 over square root of n for n greater equals to 3, right? The numerator approaches 1? No. Actually, the numerator goes to infinity also. The numerator goes to infinity. Okay, it's bounded below by 1 for certain n. Okay, so this series here is bounded below by the series of 1 over square root of n, right? Okay, now which is divergent by p series p equals to 1/2, which is less than 1. Okay, so by comparison test, the series is divergent. Okay, but the alternating series of that series is convergent according to what we have here. Sorry. Yeah, according to what we have here, it's so this series basically this series is conditionally convergent. Okay, the way you study, if every time you see alternating series, right, ask yourself, is it conditionally or absolutely convergent? Okay, that's for number 19. Can you pick one more question? I remember I worked very hard for that number 36. Let me try it again. I knew I finally found it, but I don't remember how. Number 36 and number 38, I think. Let me try again, number 36. If I get stuck, I'm sorry, but at least I'm basically done with what I want to do today. No, I'm sorry. We are not done with 1.7 yet. I would like you to actually start working on problems from 1.7. Okay, so on Wednesday, we will continue with this 1.7. However, let me try to attack number 36. I forgot what was the reason I get stuck. And I remember later on, I actually found it, but let's see. So natural log of n to the power of natural log of n is equal to, let me make it e to the natural log of n to the natural log of n. This is equals to e to the natural log of n times natural log of n. This is e to the natural log of n to the power of natural log of n. This is n to the natural log of n. Oh, I remember now. And we know that natural log of n will be positive, will be greater than 1. For some n, actually I need this. So hold on. So it's basically saying the following. So because this guy here equals to this, so 1 over natural log of n to the power of natural log of n is equal to 1 over n to the ln of ln n. Now, all I need is actually this exponent. I need to show that this exponent here is eventually more than 1. Okay? It's eventually more than 1. For some first couple terms, it will be finite anyway. Okay? But in the long run, the ln of ln n will be greater than, let's say, 1.5. Okay? Let's set it up that way. Let's set it up that way. So note, let natural log of n to be greater than, choose a number greater than 1. Let's say 1.1. Okay, so natural log of n will be greater than e to the 1.1. Okay, so n will be greater than e to the 1.1. You see what I mean? So, and it doesn't have to be 1.1. You can make it 2 if you like. You know what? I make it 2. I make it 2. Why, Thomas? So that it's easy for me to compute. Lazy guy. Right? So let me choose that to be 2. Okay? So this is e squared. This is e to the e squared. Okay? Let me make this n. The n has to be greater than that. Right? Okay, let me make it, let n to be greater than 3 to the 3 squared. What do you think? Which is 3 to the 9th. Is it good enough? Okay, so basically I'm saying the following. This series here from 2 to infinity of 1 over natural log of n to the natural log of n, this guy is equal to the series from 2 to infinity of 1 over n to the natural log of n, right? But this is the series from 2 to 3 to the 9th of 1 over n to the ln n natural log of n plus from n equals to 3 to the 9 plus 1 to infinity of 1 over n to the natural log of n. But this guy will be bounded above by basically I change it into P series. 1 over n squared. Right? Okay, but is convergent by P series P equals to 2. So by comparison test, let me continue here. So by comparison test, the series from 2 to infinity of 1 over natural log of n to the power of natural log of n is convergent. Oh, finally I did it. Yay, surprise. Number 37, I know is on the easy side. Number 38, I don't think so. So let me try to attack number 38. Oh, by the way, I need to, this is you choose any number. Choose any number greater than 1. Okay, so you can use 1.1 and just use calculator from there. Okay, so should I have used 1.1 like earlier? Let me use my calculator to compute. E to the 1.1. That is 20 something. Oh, wow. So this is 20 point something. So just use n is greater than 21, right? You don't need to go that far. Just use n greater than 21. But then you will have the bounded here, the bounding here will be instead of 2, you will get 1.1. But that's enough, right? That's enough. Once the p is greater than 1, then it is convergent. Okay, so you don't need to go up to a very big number. You can just go up to 20. And this start from 21, like that. You see what I mean? You just need to find, if you choose 1.1, there will be an n where, if you choose 1.1 instead, then there will be an n where this is true after such n. Okay, so when you use 2, there's another number. Actually, if I use 2 here, this is already greater than, I can just use n to be 1619, for example. Okay, if that's a 2. But 3 to the 9 is a very big number. It's much larger. Okay. Well, anyway, that's just technique. That's just a technique. I mean, you can always choose such n such that any term after that n, it will be convergent, bounded above, right? Convergent because of the p series. Okay, I guess I will just stop here and I will think about that number 38. Okay, see you then.